Very good. So, hello everyone, and we are into the third and final week of our Les Houches online summer school. And well, you know me. I mean, normally the moderator of this morning session would have been Professor Kawasaki. I don't see him online yet. I mean, there could be a reason, but nevertheless, let me introduce you to Professor Takagi, who is very well known and who is currently spending 100% of his time in Stuttgart due to the current epidemic. And so this morning, he will give us the first of his two lectures on quantum spin liquids. So his presentation will be 90 minutes. And those of you who have questions, please use the chat feature to write them. And depending on time, at the end of the hour and a half, then he will answer your questions. I see that our moderator is coming online, so now he will probably take over. Okay.
I'm sorry. Takagi-san, I'm sorry.
No, it's okay. So, all right. Well, so now you're the moderator, and I have sort of given a very, very brief introduction to Professor Takagi, but maybe you can, I mean, you had prepared something, so you may say a few words about him.
Okay. Yes. Welcome back to the lecture of Professor Takagi. So, Mark, did you introduce him? Let me introduce.
I said very little, so.
Okay. Yeah, let me introduce him. He's a professor at the University of Tokyo, but at the same time, for probably his major affiliation is now Max Planck Institute, as you see in his biograph. And he got a PhD from University of Tokyo. Then he spent a few years in AT&T Bell Laboratories. And then he had been a chief scientist at RIKEN for about 10 years. Then he moved to Max Planck. And he have received major recognition like Cameron Honest Prize and Humboldt Professorship, and recently Eugene and Ziebold Prize? Okay, I'm sorry. Yeah, okay. He's a quite famous and professor in quantum materials. And for the audience, please use a chat function to give him questions so that I or Professor Takagi can see. And today he is supposed to give a 90 minutes lecture. And the second day he will give a 75 minutes lecture plus 45 minutes Q&A. But today, during this 90 minutes lecture, if I see very important questions in the chat, I will name you, and Professor Takagi will be kind enough to respond to your question. Okay? All right, so yeah, please, Professor Takagi, please go ahead.
Okay, so thank you very much for your introduction, Kawasaki-san. So yeah, since I do see 20 people online, so with that number of audience, I can be fully flexible. So you can bother me anytime. Okay. So So today, I'm going to talk about, first, part of my lecture on quantum spin liquid. Let's see. why it doesn't move. Okay. So yeah. So let me introduce myself. I'm a material physicist, and my job over 35 years has been to hunt exotic electric matter formed by correlated electrons in many cases in transition metal compound, particularly oxide. That's my job. And I have been searching for, exotic phase of correlated electrons, like electron solid, liquid, gas, sometimes, super fluid. That's often called superconductivity, electron liquid crystal. And since, electron has, charge, spin, and orbital degree of freedom, and often they behave independently. For example, charge, solid, but spins a kind of liquid state called spin liquid, or, orbital liquid. And I'm kind of happy if I can find the phase as exotic as possible. And among those exotic phases, so-called quantum spin liquid is my favorite exotic phases. And those two lectures, I would like to devote my time, mostly on quantum spin liquid. And concept of quantum spin liquid, came from a study of low-dimensional magnet, particularly one-dimensional anti-ferromagnetic chain. Then people try to implement concept in 1D chain physics to 2D, and developed so-called RVB type quantum spin liquid in 2D. And that's kind of my main topics. And recently, a new type of quantum spin liquid has been attracting considerable interest, called the Kitaev quantum spin liquid. And today, I want to talk mainly about the 2D RVB type quantum spin liquid, starting from 1D concept, and in particular materials. And tomorrow, I would like to speak about quantum spin liquid from a slightly different angle. So tomorrow, I would like to discuss, electron correlations and spin-orbit coupling. And I'm gonna, tell you, the spin-orbit coupling stabilizes Mott insulator, and there, we can have, 2D quantum spin liquid and other exotic, phases. And at 2D Kitaev quantum spin liquid, 2 days lecture meets. Okay, so that's kind of a big, plan. And today, let me speak about quantum spin liquid, from 1D to 2D, focusing on RVB type quantum spin liquid. So here is outline today. And first, let me clarify what is quantum spin liquid, with emphasis on so-called RVB type quantum spin liquid on two-dimensional triangular lattice. Then since I'm experimentalist, so I would like to materialize quantum spin liquid, and let me talk about kind of a survey of materials which could be a good candidate for quantum spin liquid in 2D. And I'm going to talk about kind of case studies in 2D material with two-dimensional triangular lattice. Then I'm going to speak about the quantum spin liquid candidate with 2D Kagome lattice. Okay, so that's kind of big plan of lecture today. Now, so first let me speak about what is quantum spin liquid. And suppose we have Mott insulator, 1 electron per atomic orbital, like this. Okay, and 1 electron localized, okay, on each atomic orbital. Okay, so it's insulator, Mott insulator. Now you can have two kinds of spin configuration: up down, up up, and if neighboring spins parallel each other, ferromagnetic, okay, because of Pauli principle, exclusion principle, the spin 1 cannot travel to site 2, okay. But in case of anti-ferro configuration, because of the opposite spin, okay, this spin, up spin in site 1 can travel to site 2, which cost of Coulomb on-site Coulomb repulsion U. Okay, and if you consider this process perturbatively, anti-ferro configuration can gain this perturbation energy scaled by T square, hopping energy divided by Coulomb U. So therefore, in most Mott insulator, spins are interacting anti-ferromagnetically. And Coulomb U is of the order of electron volt, and the transfer is of the order of 0.1 electron volt. Okay, so therefore, in many transition metal oxides, this anti-ferro interaction is of the order of 100 to 1000 Kelvin, 10 milli electron volt to 100 milli electron volt. And with this anti-ferro interaction for Mott insulator, so if local spins on top of squared lattice like this, of course you can form anti-ferromagnetic ordering, up down, up down. This is energetically favorable, and this breaks symmetry. So you have magnetic ordering, anti-ferromagnetic ordering with spontaneous symmetry breaking. So this situation you might view as solid state of interacting spins. But if you place anti-ferromagnetically interacting spin on top of triangular lattice, story different. Okay, here you have anti-ferromagnetic pair, gaining in energy, but this side, okay, if you place it up, okay, you can gain energy for this bond, but you lose energy for this bond, because of ferro configuration. So therefore, you cannot find one specific way of minimizing energy. Okay, so you have to kind of compromise, but there are many ways to compromise, and this is often called the geometrical frustration coming from triangles, and this frustration suppress long-range ordering, spontaneous symmetry breaking. And if this frustration is coupled with quantum effect, the ground state could be liquid state, quantum mechanically fluctuating state of spin. And this was first proposed Phil Anderson more than almost 50 years ago. So this is a kind of textbook definition of a quantum spin liquid. So conventional magnet, you have, ferro, anti-ferro ordering, broken symmetry, and spin entropy is quenched at the transition. But quantum spin liquid, you don't have, any magnetic ordering, no symmetry breaking, and that remains, quantum disorder, highly entangled. And spin entropy, gradually decreased to T=0 limit. And as I will speak, later, there are more than one kind of quantum spin liquid. And when I talk about quantum spin liquid, I often receive a question, okay, if there is a no phase transition, no ordering, what's fun to look for quantum spin liquid? And in some sense, quantum spin liquid state, no ordering, it's kind of a state of nothing, which is central dogma for Zen. And since I'm a graduate of Buddhist high school, so somehow I like Zen concept, state of nothing. That's why I'm kind of amazed. And this is a kind of picture of Zen temple and representing nothingness. But if you take a look at this garden, okay, there is hidden topological pattern. And Zen concept said, go to state of nothing, you see hidden reality. And the hidden reality in this case is exotic elementary excitation. Okay, under the sea of quantum mechanically vacuum spin, we have hidden reality, exotic elementary excitations, and as I will tell you later, that's fractionalized spin called spinon, or some cases Majorana fermions. Okay, so look like nothing, but there is kind of a hidden reality. That's why quantum spin liquid state is exciting. And why quantum spin liquid is stabilized by quantum in fluctuation. Okay, so let me give you some microscopic picture behind the quantum spin liquid. Okay, so and I can first show you anti-ferromagnetic ordering, like up down configuration of spins. It's not very stable against quantum fluctuation. And if you have Heisenberg type anti-ferro interaction between spins, with this up down configuration, you can gain energy only for G component. Okay, so unlike ferromagnet, anti-ferromagnet is not that stable. And in fact, if you consider two anti-ferromagnetically coupled spins, so you have four possible state for spin configuration, and as you know, this two anti-ferromagnetically coupled spins, okay, with interaction, split into singlet state expressed by this formula, superposition of up down up, and spin triplet configuration up down and up down plus down up. And as this is elementary quantum mechanics. Spin singlet state gains energy of -3/4 J, and the triplet state gains quarter J. That's actually you can find in a textbook. Okay, and the anti-ferro state, like up down situation, is a superposition of triplet this configuration and singlet, right? So therefore energy for anti-ferro only up down, no quantum fluctuation, is -quarter J. okay, average of those, two energy. Okay. So therefore, as you see, spin singlet state has, lower energy than, up-down, anti-fellow configuration. And this, people often call this anti-fellow up-down state is, unstable against, quantum fluctuation. Okay, quantum fluctuation means a superposition of different, quantum state. Okay, so yeah, so that's kind of a very basic. So anti-fellow is not, so stable against, quantum fluctuation. In fact, early days of magnetism, people discussed, anti-ferromagnet may not exist. But of course, famous Nell, found the anti-ferromagnet. Now, this, instability of, anti-fellow ordering against, quantum, fluctuation is, quite, clear in case of one-dimensional anti-fellow magnet. Okay, that's quite easy to show. Okay, so this is, one-dimensional, Heisenberg, anti-ferromagnet. Okay, with interaction, like this. Okay. And if, you have, anti-fellow, like, configuration, okay? So each bond, you can gain energy of J square, okay? Because, energy gain is coming only from G component, okay? So you can gain, minus, quarter J for each bond. Okay. Right. So yeah, and there are n bond. Okay, but of course, each bond is shared by two spins. So there is factor G is number of bond coordinated, and each shared by two. So therefore you have n times G coordination number divided by two, shared by two spins. Okay, that's kind of number of bond, gaining energy. And in case of one-dimensional anti-ferromagnet, of course, you have kind of two bonds, Z equal 2. So therefore, you have, bond equal to number of spins, n. And each, bond, gains, quarter J. So therefore, energy gain is, a quarter Nj. But if you distribute spin singlet, bond, okay, like this, okay. So now, spin singlet, bond, they can gain 3/4 J, okay, 3 times, bigger, okay. And but of course, each spin can form only one bond, okay. Unlike this case, they can form only one bond, and the one bond is shared by two spins, right? So therefore, each spin has one bond shared by two spins, so divided by 2, okay, and gain 3/4 J. So in total, this configuration, you gain energy of minus 3/8 Nj. Okay, and clearly, because of 3 times larger gain for spin singlet, energy for spin singlet state has lower energy than anti-ferromagnetic ordering. And because of this, so this is kind of a superposition of two different anti-ferro configurations. So this configuration unstable against quantum fluctuation, and other ground state, quantum mechanically disordered state is realized. Okay, so therefore quantum spin liquid should be favored. I wanted to show you a bit, better, real space picture of what is quantum spin liquid. But, by talking to many kind of theorists, in case of 1D Heisenberg, it's quite hard to show real space picture. Okay, but maybe, next paragraph, you might get, some idea, what is, quantum disordered state. Okay. So in 1D Heisenberg or 1D, anti-ferromagnet, elementary excitation is, very much different from conventional spin excitation called magnum. Okay, where you have, well-defined energy versus, momentum relationship. Okay, so suppose you flip spin here. Okay, so this spin used to be down spin, and you just flip spin. So spin changes from -1/2 to 2/2. So there is a spin change of s equal 1. So this is s equal 1 excitation, bosonic excitation. And in case of, and by flipping this, okay, you have, two domain boundaries with two neighboring spins. But in case of 1D, this is kind of specialty of 1D, okay? Those kind of two domain boundary can move towards kind of opposite direction without, costing any energy, okay? So this, domain boundary can move around freely. And this we call, spin-wise excitation, fractionalized. And those kind of domain boundary, you notice, carries, spin 1/2, degree of freedom. And they behave like, fermions, okay? So this, we may say, in a one-dimensional anti-ferromagnet, spin-wise excitation fractionalized into two free-moving domains with, spin 1/2, fermions. And this spin 1/2 degree of freedom is often called spinon. And this, exotic excitation called spinon, okay, behaves, very much, different from, kind of magnum, okay. And they form, if you measure excitation spectrum, you do see a kind of a continuum excitation, okay, rather than, line of excitation. And then, in case of, Heisenberg, it's hard to give you kind of a pictorial image of what it is. But in case of XY, so if you have only spin component X and Y direction, using, Jordan-Wigner transformation, so-called, okay, even I can do that. This spin Hamiltonian is transferred into this, Hamiltonian. Okay, so this is kind of hopping, tight binding type of, Hamiltonian with, bandwidth of J. Okay, and this, fermion can be viewed as spinon. So therefore, this, with help of mathematics, can be viewed as, ensemble of, kind of fermions with, dispersion J cosine K. Okay. And those, band of, spinon fermions are kind of half-filled, okay? So this is just like a metal. And they have, fermi momentum at, half pi, minus half pi. And, below energy equals 0 is kind of occupied by fermi, just like metal. Okay, so therefore, this quantum spin liquid for 1D XY can be viewed as, C of, spinons, domain boundary fermions. Okay, that is kind of, one of picture to view quantum spin liquid state. Okay, so like on the XY case, the system can be expressed in terms of non-interacting fermions, called spinons. Okay, and they have kind of Fermi surface. Okay, and those spin one excitation, okay, can be expressed as particle for excitation of this spinon band. So the excitation, like electron excitation in metal, and so you have zero excitation at q equals 0 and q equals pi, from kf to minus kf, here. So that give like to zero excitation, and you have bunch of excitation from here to unoccupied. Okay, so that forms kind of continuum. So this is exactly like continuum of electron excitation in metal. Okay, so this continuum, because of spinon, is a hallmark of quantum spin liquid. And in fact, measuring neutron. Okay, so you excite S equal 1, but decay into 2 spinons. Okay, so you see kind of a continuum of excitation. Okay, like this for one-dimensional Heisenberg magnet. Okay, or recently, you can measure magnetic excitation using inelastic scattering called LIX, and again you can see spinon continuum here. Okay, so in 1D, quantum spin liquid, quantum disordered state, and spinons at elementary excitation is well established. But now, I come to main topics of this lecture. How about 2D? Okay, and at the end of the day, I would like to say, we can have, similar physics of quantum spin liquid, fluctuation of spins, even in 2D, if specific geometry, like triangular geometry, is involved. Okay, that's kind of a story. So, of course, in higher dimension, okay, anti-fellow ordered state is more and more stable. For example, in case of scaled lattice like this, okay, now unlike 1D case, you have 4 bonds per spin. Okay, so you have 4 neighbors, 1, 2, 3, 4. Okay, instead of 2 in 1D. Okay, so therefore, you gain energy doubled, okay, because G is kind of doubled, and this state, anti-fellow ordering can gain roughly half J per spin. Okay, this is due to increase of number of bonds. Okay, so although we can gain energy only for G component, but because of the increase of a bond, you can gain energy more. But in case of singlet, bond, okay, so since each spin can participate in only in one bond, okay, so therefore number of bond you can gain energy doesn't increase even in higher dimension. Okay, so again, energy gain is scaled by number of spin moment. Okay, so they gain 3 quarter shared by 2 spins. So the energy gain is the same as one-dimensional case, minus 3/8 times J. Okay, now anti-fellow configuration has lower energy than singlet. Okay. So therefore, in 2D, in general, anti-fellow configuration is, better stabilized. But as Phil Anderson pointed out, okay, so if you have, geometrical kind of frustration, the story would be different.
Takagi sensei.
Yes.
Yeah, you got the 2 questions here.
Oh,
If
okay.
you don't mind.
Thank you.
Can you see the chat?
Okay, so question is XY model coming to play. So yeah, because yeah, so of course I wanted to speak about XYG or Heisenberg, but this case this spin-on language is extremely complicated. But in case of XY, you have spin liquid ground state, but because of you have only X and Y. Using Jordan-Wigner transformation, spin Hamiltonian is mapped onto very simple Hamiltonian, tight binding style Hamiltonian. That's why I introduced the XY model. Okay. And the next question is, yeah, am I answering your question? If I misunderstand, could you turn on the microphone and ask me directly? Next question is for conventional magnons. Q vector could be interpreted as a length scale of spin flip. Yeah, I think so. Yeah. So like, so you give a kind of a Q vector, but since you create 2 spin-ons, okay. So there, you get 2 spin-ons, right? Maybe let me show you the view graph. Somehow my PowerPoint is very slow. I don't know why. Yeah, okay. So the question is, yeah, in case, yeah, so in case of spin-on, yeah, so you create, S=1 excitation and with, momentum Q, but, they kind of split into kind of spin-ons, okay? So therefore, the kind of a center of mass momentum is, Q for 2 spin-ons. But of course, there are kind of many choices for 2 spin-ons, like K and minus, K plus Q. Okay, and you have, different K. That's why, you have, continuum. And the next, question is, yeah. So quantum spin liquid is only for XY. No. No. Yes. Yeah. Sorry, actually it was Japanese. Yes. Yes. Heisenberg case ground state is known to be quantum spin liquid. Yeah. So
can I just maybe ask directly? If that's okay.
Yeah. Yeah. Sure.
So,
I think that's easier.
Yeah, for the 1D case, because I was having a hard time imagining how can I have a spin liquid in 1D. And let's say for 2D, I can imagine some sort of frustration, and then I can't really define the ground state. So I didn't really understand how this XY model results in a 1D spin liquid. So if maybe I missed something, but yeah.
Yeah. Okay. So that's I can answer quite easily. Okay. So so this triangular geometry, okay, because of conflict of 3 bond, reduces energy you can gain for antiferro ordering, right? So antiferro is destabilized in case of a triangular lattice because of geometrical frustration. But in case of 1D, they have only 2 bonds. Okay, so like a reduced dimension is destabilizing antiferro ordered state. Okay, so that's why quantum spin liquid is kind of favorable for 1D. Did you get the point?
I think so. So you don't have frustration, but because you have these excitations.
No. Actually, frustration is one of the cause.
Okay. So
Okay.
the main point is the excitations I have for the ground state, the magnons.
No, really, because the question is whether quantum mechanically fluctuated state is kind of more stable or not compared with the antiferro.
Okay, I see.
Normally,
I
in
get
high
the point.
dimension,
Okay.
antiferro can be stabilized because they have many bonds. Like in a 3D cubic lattice, right? You have 6 bonds, right? But in case of 1D, you have only 2 bonds. That destabilizes antiferro. That's why quantum disorder state is kind of favorable. As you see this view graph, right? So this singlet state, okay? The energy doesn't depend on geometrical configuration and the dimension, okay? They are determined only by number of spins. But this antiferro configuration, the energy depends on dimension, like a one-dimensionality or geometrical frustration. And in a specific situation where dimension is reduced, geometrical frustration is involved, antiferro is kind of destabilized. That's why quantum spin liquid is kind of stabilized. Am I clear?
Yes, I got your point.
Okay,
You don't have to have frustration necessarily. Thank you. Thank you.
Good. Sorry, I'm in trouble in changing my slides. So let me stop sharing my screen for a while. Okay, and maybe let me stop some of. Okay. Okay. Okay, and also there was another question. XY model is the only model which gives rise to quantum spin liquid. Actually, no. 1D Heisenberg, ground state is quantum spin liquid. But if you have SG component in this Hamiltonian, okay, can you see my pointer? Okay, so if you have SG here, in this Hamiltonian, okay, made of spinons, you have interaction term, okay. So therefore, in case of Heisenberg, you have to deal with interacting spinon, okay. So it's like a correlated electron, And so therefore, it's kind of hard to represent the state in case of Heisenberg. Okay, that's why in order to give you a kind of intuitive picture, I avoided Heisenberg and used in XY. Only in the case of XY, you have non-interacting spins, kind of hopping. Okay, and there, because spin-ons are non-interacting, you can easily get kind of a picture behind. Okay, but it does not necessarily mean that in case of Heisenberg, quantum spin liquid is not stabilized. Okay, so in case of Heisenberg, you have quantum spin liquid of interacting spin-ons. Okay, so in that sense, the problem is kind of a deeper. Okay. Okay. Any further question? Okay, and can you see my screen now?
Yes, we can see it.
Okay, good. Okay, now it's moving. Okay, so
yeah, okay.
Okay. So and there's a okay. So this figure is related to the kind of question, and so because of those kind of three bonds, okay. So two gain energy, one lose energy. So in case of triangular lattice, because of frustration, energy gain is reduced by a factor of 1/3. Okay, because this bond and this bond, energy gain kind of cancel out. Okay. So only one bond out of three can gain, energy, right? So therefore, in case of two-dimensional triangular lattice, okay, so you have, 6 neighbors, okay, for triangular lattice, okay, much larger. But because of a geometrical frustration, okay, energy gain is, reduced to 1/3. Okay, as a result, you gain only minus, quarter J, okay? The same as, one-dimensional antiferromagnet. So therefore, antiferro for triangular lattice is quite, unstable. And again, singlet case, you gain, minus 3/8 for singlet, okay? So therefore, this state is unstable against, quantum fluctuation, okay? So that's why people expect, we might have, quantum spin liquid in 2 dimensions because of geometrical frustration. But in reality, okay, so if you allow spin kind of rotate, okay, so you can form so-called 120-degree structure of S=1 spins, okay? And if you have, this, 120-degree non-collinear configuration, okay, because of tilting of spin, okay, your energy gain, due to, antiferro ordering is, only 50%, okay? But this case, all the bond can gain energy 1/2, okay? So therefore, this is kind of factor of 3. And this is, factor of 1/2. So therefore, this configuration, you can gain energy minus, 3/8. Okay. So in that sense, triangular lattice, it's quite delicate. Okay. Whether quantum disorder state is kind of favorable or not. Okay. But Anderson pointed out that by having a superposition of different singlet state or coupling lattice, this state could be stabilized on a triangular lattice. That's the argument of Anderson. This is kind of a picture of Anderson. Okay, so how to distribute singlet bond? Maybe you can make a lattice of a singlet bond. Like this. Okay. And this case, because of ordering, symmetry is broken. So this is not, quantum spin liquid state. But this, can be accompanied with some sort of lattice deformation, forming a kind of a dimers. Okay. And with, lattice, this state might be realized. And this state is kind of ordered state of spin singlet, and called, valence bond in a solid. Okay. Solid state of, dimer spins. Now, on the other hand, you can distribute, those singlet pairs randomly on top of triangular lattice. And there are many ways of distributing. Okay, macroscopy demonstrates in many ways of distributing a singlet bond over the space. Okay, and let's kind of superpose, different distribution of singlet and sum up. Okay, so this state, state are kind of quantum mechanically fluctuating from, these 2Ds. Okay, and because of a superposition, this state might be kind of stabilized. Or maybe, not only, next nearest neighbor singlet bond, but you might consider kind of long range singlet, bond. Okay, and again, you can form a superposition of different, configuration of singlet bond. Okay, and since this, singlet pair is formed by, next neighbor, so this situation is called short range, resonance, valence bond state, RVB state. So short range RVB quantum spin liquid. Okay, and this, you have, long range, pair of spins, and this, state is, called long range, resonance, valence bond state, quantum spin liquid. Okay, and since you have kind of superposition of different state, overall symmetry not, block. Okay, so this is kind of an image of, quantum spin liquid on a triangular lattice. Okay. And let me think about the excitation. Okay, in such, quantum spin liquid on two-dimensional triangular lattice. Okay. So yeah. So in case of valence bond solid, so you have kind of dimer molecules on top of triangular lattice, and you just create S equal 1 excitation from a singlet to triplet, and that's all. So no fractionalization. Okay, and the S equal 1 excitation has kind of a gap, and perhaps small kind of dispersion. So this case is classical. So this we don't call it quantum spin liquid. However, in case of RVB quantum spin liquid, short range and long range, okay, create S equal 1 excitation, okay, and those S equal 1 excitation, okay, because of those kind of random distribution of singlet pair, okay, can decompose into free S equal 1/2. And therefore, this quantum disordered state, you have, spin-on S equal 1/2 spin-on excitation, okay, fermionic excitation as, an elementary excitation. And in case of short range RVB, okay, since, you have to cost, finite energy to break up singlet, pair. So therefore, you expect some sort of excitation gap in spin-on excitation. But in case of long-range RVB, so you have, quite a weak bond. So therefore, this case, you can have, zero energy excitation of spin-ons. Okay. And in some cases, with this gapless situation, you might have Fermi surface of spin-ons, like XY model I discussed. Okay, so therefore, 2D quantum spin liquid okay, with, long range, RVB, you have, metal like, continuum response if you do neutron scattering spectroscopy. But in case of short range RVB, was zero energy excitation is kind of missing, and you expect to have some sort of a gap in the excitation. Okay, but from this, it is clear. Okay, if we have quantum spin liquid, there could be more than one kind of quantum spin liquid, like with excitation gap, without excitation gap, with Fermi surface of spinons. Okay, so quantum spin liquid is not only one kind. Okay, then I have to mention in case of triangular lattice, later study, okay, including this work by David Hughes, they showed in case of triangular lattice, if you consider only nearest neighbor anti-ferro coupling, this 120-degree state has lower energy than RVB quantum spin liquid. So therefore, only nearest neighbor coupling, ground state is 120-degree anti-ferro state. Okay, as I said, their energy is almost equal to quantum spin liquid state, and detailed calculation shows only only nearest neighbor interaction, you have 100-degree structure as a ground state. But still, theorists believed with additional ingredient like long-range interaction, like next nearest neighbor interaction, higher order correlation, like Houches correlations, higher order correlations, or anisotropy, coming from spin orbit coupling, could stabilize quantum spin liquid, okay, on triangular lattice over 100-degree ordered state. Or theorists argued with other geometry, like Kagome. Okay, Kagome has reduced coordination number. Quantum spin liquid could be stabilized, and theorists paid a lot of effort. And I think now consensus is theoretically those statement is highly likely the case. So if we have additional ingredient or different geometry, in principle we can have quantum spin liquid state in 2 dimensions. Okay, and we are kind of experimentalist. Maybe final proof is to find such 2-dimensional quantum spin liquid state experimentally. Okay, that's why we experimentalists are kind of excited about this business. Okay, so let me check chat. Okay, so thank you. Okay, now. Yeah, so now it was Toyo theorist before, but now we experimentalists would like to bring it to reality. And now question is can we materialize spin 1/2 Heisenberg antiferromagnet with triangular motif, and can we realize quantum spin liquid state there? And there, we really do not see any phase transition. Can we see continuum excitation there? That's kind of a question to ask. Okay, and in fact, in the last 10, 20 years, I think experience did very good job. And this is all the review by Patrick Lee. But somehow we are about there. And the existence of a quantum spin liquid, in materials are about there. Okay. So let me give you a kind of example. Okay. But before showing example of real quantum spin liquid candidate, let me briefly mention about what to do to identify quantum spin liquid. Okay, so in general, okay, so we want to make that kind of lattice of spin or half spins, like triangular lattice. Okay, so this has 6 coordination number. And the 2D Kagome lattice, this case you have only 1, 2, 3, 4 coordination. Okay, so much smaller than triangular lattice. Okay, so therefore we might have much better chance for Kagome to find quantum spin liquid. Well, we may go even 3D. If we have so-called a pyrocular lattice, corner shared tetrahedron. Okay, so you have 6 bond like a triangular lattice. So though it's kind of higher dimension, but coordination number is the same as 2D triangular lattice. So we can have a chance of finding a quantum spin liquid there. And in fact, making a triangular motif in a real material, might be easier than you might think. And for example, we can make triangular lattice easily from famous cubic sodium chloride structure. Okay, so this is sodium chloride structure. Okay, and this looks like a quite cubic, white triangle. So why don't you take a look at this sodium chloride structure along 110 direction, diagonal direction. Then you can see, along 111 direction, you have a pileup of triangular lattice made of sodium, chlorine. Okay. Well, so this is kind of picture from 110 direction. Okay. So and maybe instead of sodium chloride, let me say magnetic nickel and non-magnetic oxygen, nickel oxide. Okay, and yellow nickel, blue oxygen, right? So you have first oxygen triangular layer, and the next one is nickel triangular layer, and below is again oxygen triangular layer. Okay, so therefore nickel is magnetic, and you have triangular lattice of nickel here, sandwiched by triangular layer of oxygen. And you can see this nickel is coordinated with the 6 oxygen, forming octahedron like this. Okay, so you have kind of triangular lattice made of nickel oxygen 6 octahedra. Okay, so as I said, it's kind of a piling up of triangular nickel lattice and the oxygen lattice. Okay, but it's kind of still 3D. But if you replace, like a nickel layer with a non-magnetic ion, like lithium, for every 2 layer, you can isolate triangular nickel lattice like this. Okay, and make magnetic 2-dimensional triangular lattice. Okay, or consider again cubic sodium chloride structure, and those sodium ion, as you can see, form a tetrahedron. And if you take tetrahedron, connected by the corner from sodium chloride lattice, you find the so-called pyrocular lattice. Okay, so actually pyrocular structure is closely related to sodium chloride structure. So actually it's quite common in nature. And besides this pyrochlore structure, if you see very carefully, along a 111 direction, okay, again, so you have a pile up of this layer and this layer. And this broken line layer is triangularis, okay? And this blue layer, as you see, is a Kagome layer, okay? So pyrochlore structure is a stack of triangular layer and the Kagome layer, okay? So therefore, if you replace a triangular layer with non-magnetic ion, you can make a Kagome magnet. Okay, so therefore, from a materials viewpoint, this triangular-based structure is not rare at all. Okay, so we have a very good chance of finding them in nature. And how to characterize, right? So maybe once you make a material with triangularis, you first measure magnetic susceptibility. And you see Curie-wise behavior at high temperature, and confirming local moment there. And from Curie-wise temperature, what is scale of interaction. Okay. And so this is kind of a cartoon picture. So if you plot 1 over chi as a function of t, okay, Curie-wise behavior gives us a kind of straight line. Okay, and this intercept, temperature is Curie-wise temperature. Okay, negative is kind of anti-ferromagnetic, and in classical anti-ferromagnet, okay, magnetic ordering takes place around the Curie-wise temperature, mean field transition temperature. Okay, but if frustration works, this long-range ordering kind of suppressed. And long-range ordering takes place much lower temperature than Curie-wise temperature. Okay, so therefore you can view the ratio of Curie-wise temperature and the nail ordering temperature, the ratio, as a measure of frustration. Okay, if frustration is stronger, this ratio goes up. Okay, and the quantum spin liquid no nail ordering. Okay, so that means this frustration factor infinite, and you see Curie-wise, but you don't see any magnetic ordering. Okay, and of course magnetic susceptibility is not a very sensitive probe to magnetic ordering, and you should confirm absence of ordering by NMR, neutron, X-ray, muon spin rotation, or specific heat. And once you find the absence of ordering, you want to identify elemental excitation. And the easiest is to see magnetic susceptibility. And if you have gapless spin liquid, you have something like Pauli susceptibility. So you have finite susceptibility at t equals 0 limit. But if you have spin liquid with gap, okay, then susceptibility goes to 0 exponentially. Okay, that's how you can identify gap. And of course, if you have spin-on Fermi surface, gapless, of course you have finite susceptibility. At the meantime, if you measure specific heat, like metal, 0 energy excitation give rise to T-linear specific heat. So you should have finite T-linear specific heat in case of gapless quantum spin liquid. And nowadays, everybody interested in measuring thermal conductivity, and thermal conductivity is a product of heat capacity times mean free path. Okay, so therefore this thermal conductivity measures kind of spin-ons, which is itinerant. Okay, so in that sense, nowadays this thermal probe is quite important. And of course, finally, you measure neutron scattering, and you would like to see whether spin excitation kind of fractionalized into spin-on or not? And do you see continuum excitation like this? Okay, that could be kind of a quite important check. Okay, with this in mind, okay, let me give you case studies for quantum spin liquid candidate. And let me begin with a two-dimensional triangular antiferromagnet. Okay, first I would like to speak about those two specific compounds, which I believe most promising candidate for quantum spin liquid. Okay. So I cannot explain all the details of those kind of molecules, but as you see, okay, so you have two BDT molecule, okay, and there is anions, okay, and those BDT molecule, okay, form dimer, okay, like this. So this is a BDT TTF2. That's dimer molecule, and then those dimer molecule forms a kind of a lattice like this, and forming layers. Okay, and this anion want to be -1. Okay, so therefore they take one electron from dimer molecule. Okay, so originally they had two electrons in antibonding band, but anion takes one electron from antibonding band. So as a result, those dimer molecule, you have one electron in antibonding band. And since overlap between kind of molecule kind of relatively small, they form S equal 1/2 multi-insulator. So one S equal 1 moment on top of this dimer molecule. Okay, that's why those organics are S equal 1/2 magnet. Okay, and with this lattice, you have two kind of interaction, solid line and dotted line, and each bond you have overlap integral like a transfer integral T, okay, and the dotted line T prime. Okay, and as I mentioned earlier, antiferromagnetic coupling is T square over U. Okay, so therefore antiferro coupling is in proportion to square of transfer energy. And for those compound, by chance this T and the T prime is almost equal. So that means magnetic coupling J is almost equal for this solid bond and the dotted bond. And as a result, those spin 1/2 is connected by almost equal J antiferromagnetic, and J form triangular lattice. That's why we have S equal 1/2 triangular lattice for those organics effectively. Okay. And so here is NMR data for those two organic S equal 1/2 magnet. Okay, and this is kind of NMR spectrum. This represents kind of a distribution of magnetic field. Okay. And as you see, there are kind of two lines, but no change down to lowest temperature. That means no magnetic ordering. Okay. But like this compound, okay, this T and T prime is unequal, and so therefore you have strong bond and weak bond. So it's not triangular lattice anymore. And in that case, with lowering temperature, you can see this line, okay, distribution magnetic field split into many peaks. That means you have magnetically inhomogeneous environment. That means magnetic ordering. Okay, so this you do see magnetic ordering, but this you don't see magnetic ordering down to 30 millikelvin. Okay, And the energy scale of magnetic interaction is over the order of 200 Kelvin. Okay, so and this is almost a 4 magnitude kind of smaller temperature, but still you don't see any magnetic ordering. And this palladium D-mit, okay, as a quantum spin liquid candidate, okay, again you don't see any splitting of peak. Okay, so at least from this you can confirm absence of magnetic ordering of a spin 1/2 moment. And here is magnetic susceptibility. Okay, and you can see Curie-Weiss behavior increasing with decreasing temperature at high temperature, but no anomaly representing anti-fellow ordering. Okay, here is specific heat. You don't see any lambda type anomaly representing magnetic ordering. Now, how about elementary excitation? Okay, so from those we confirm absence of magnetic ordering. It's likely quantum spin liquid. Then let's discuss elementary excitation. And as you see, okay, there is a finite susceptibility at equal 0 limit. So there seems to be a gapless excitation. Okay. Or if you take a look at the specific heat divided by temperature, okay, as a function of t square, okay, this is t equals 0 limit gives rise to a finite intercept. So like a metal, okay, so they have finite amount of a linear term. Okay, and they are insulator. Let me emphasize. But you will see some Pauli-like susceptibility or T-linear specific heat. Okay, like metal. Okay, but again, it's insulator. And let me remind you, in a weakly interacting metal, okay, so Fermi gas with a spin degree of freedom, okay, Pauli susceptibility is scaled by density of states of electrons, and the T-linear specific heat is scaled by density of states of electrons. So therefore, ratio of Pauli susceptibility and the gamma is material independent constant. Okay. Okay. So this is called the Wilson ratio. Okay. So therefore, when we take a look at the metal, we take ratio of Pauli susceptibility and gamma T-linear susceptibility divided by this material independent constant. And one means what is expected for this relationship. And in most of metal, this ratio is over the order 1. Okay, so this comes from finite density of states at Fermi level and the presence of Fermi surface. Now, suppose we have fractional spin excitation that is kind of a gapless. They have spin 1/2 moment and forming a Fermi surface. They could give rise to Pauli-like susceptibility and specific gamma T-linear. And of course, the same phenomenology can be applied. So therefore, naively, we might expect Wilson ratio for T equals 0 limit susceptibility and the T-linear term. Okay, and here actually you get something like a 3 times 10 to the -4 for T equals 0 limit susceptibility. Okay, and again this BDT. Okay, we get 13 millijoule per mole K square. it's like just like a metal. Okay, and taking a ratio of 2, we get the Wilson ratio of 1.5. Okay, and somehow my figure is kind of missing, but okay, but other case again we get the Wilson ratio 1.5. Okay, so somehow we see Pauli-like susceptibility, we see T-linear time, zone insulator, and they satisfy kind of a Wilson ratio close to 1. Okay, so they have some fermionic degree of freedom, gapless, and perhaps Fermi surface, but they have spin Arc moment. Okay, that you may describe it to the presence of spin-on Fermi surface. And maybe for your information, let me show you the case of one-dimensional anti-ferromagnet, which is kind of proven to be a spin liquid. And this is a famous spin-Arc chain compounder, strontium-2 couple 3. And you see finite susceptibility at T equals 0 limit. You have T-linear specific heat, like a triangular magnet. And since bandwidth of spin-on band is roughly scaled by J, and those copper oxide has almost 10 times larger J bandwidth. Okay, and the density of states is scaled by 1 over bandwidth. So therefore, they have much smaller chi and the gamma compared with organic case, but that's kind of consistent with much larger J. So they are smaller, but if you take a ratio of T equals 0 limit susceptibility and gamma, we get the Wilson ratio of 2.5, slightly larger than 1.5, but over the order of 1. And as I said, those spin-ons in Heisenberg, case, is kind of interacting spin-ons. And maybe, this enhancement of Wilson ratio might represent such kind of interaction. But anyway, so phenomenologically, we do see the same. Okay. And to make presence of spin-on Fermi surface more convincing, let me show you, kappa over T, okay, thermal conductivity. And if you take a look at the textbook of Kitto, okay, kappa is in proportion to specific heat, velocity, and the mean free path. Okay, so like if you take quantity kappa over T in a T equals 0 limit, okay, so you have specific heat coefficient gamma times mean free path L. So if you have reasonably long mean free path, you should see T-linear term in thermal conductivity. And this is a case for this so-called DMIT compound. And as you see, kappa over T is extrapolated to finite value at T equals 0 limit. On the other hand, other compound, BD compound, they find the kappa over T go to 0. Or that means mean free path for BDT compound is kind of much shorter or kind of localized. But this case, okay, DMIT, you seem to have mobile fermions forming a Fermi surface, giving rise to finite, gamma. And we know, roughly, what is, velocity of spins and gamma from specific heat. And from this, you can estimate mean free path of, mobile carriers, likely spin-ons. And those, also estimated mean free path is as long as 1 micrometer, huge. Okay, so you have huge nucleus like a clean metal. Okay, so from those measurements, okay, we see there is finite density of excitation at t equals 0, and likely there is a kind of spin-on Fermi surface, and those spin-ons are highly mobile. Okay, so great, right? And interestingly, if you apply pressure to those compound, likely with spin-on Fermi surface, this molten insulator melts into metallic state, and in the metallic state, they do superconduct. And both compound, you do see a continuous evolution from quantum spin liquid to metal superconductor. That's quite interesting. And some people discuss this spin-on Fermi surface insulating evolve into a real electron Fermi surface, and at the same time superconductivity. So that's kind of an exciting message from organics. So far so good, but it might be fair. There remains kind of some issue, this organic quantum spin liquid. Okay. Yeah. First of all those quantum spin liquid, there is some signature of phase transition kind of anomalies there, which we don't know why. Like this is kind of NMR and 1K, 1 over T1, nuclear relaxation rate shows a very clear anomaly. And also nuclear decay curve, shows some anomaly around this. And so there seems to be, some sort of phase, transition could be related to spin-on Fermi surface. So we do see T-linear term in specific heat and thermal conductivity. Even this BDT compound, you do see some kind of anomaly in specific heat around 6 Kelvin. Okay, this is T scale, so it's kind of 6 Kelvin. And there's some anomaly at NMR, and we don't know what. Okay, so in that sense, we don't understand that 100% yet. And recently, even more kind of a serious experimental issue was related to this beautiful organic spin-1/2 triangular system. So this is original work, okay, showing T-linear thermal conductivity. Recently, 3 groups, including original group, measured same material again, and they didn't reproduce this result, and thermal conductivity divided by T go to 0. So that means you don't have mobile excitation. Okay, and if they don't move, we are in big trouble. So we don't know what it is. Therefore, and they kind of investigated, and somehow this T-linear term is collected kind of linked to magnitude of thermal conductivity at higher temperature. That is related to phonon thermal conductivity. And their conclusion is that when phonon mean-free path is kind of long, this T-linear term tend to be larger. So in order to observe mobile carrier, you need quite clean material. That sounds natural. And they said somehow if you cool down rapidly the sample, it's kind of disordered. But if you cool down very gradually, slowly, the system appeared to be relatively clean. And they say if you cool down, relatively slowly, they find the recovery of T-linear term. So it's quite sensitive to disorder. Okay, but still, I have to admit, even slowly could sample, the magnitude of kappa over t is in only 0.02, one order magnitude smaller than the original report. So in that sense, original report has not been completely reproduced yet. So in that sense, this is kind of beautiful system, and it's kind of likely we have spin-on Fermi surface, but there remains some experimental issue to pin down all the issues. Okay, and of course you may ask me, in order to confirm spin-ons, fractionalization, we should see continuum excitation using neutron inelastic scattering. Okay, but unfortunately, those organics are full of hydrogen, and they are strongly absorbing neutrons. Scattering cross section for light element is kind of small, and it's hard to make that kind of experiment. Okay, but recently, fortunately, I think I'm supposed to stop now, Kawasaki-san, right?
Yes. You spend 90 minutes, but how many minutes do you want to? Do you
maybe
have?
So let me use 5-10 minutes, okay?
Okay, that's gonna be
rest,
okay.
I'm bring it to tomorrow. I'm gonna change the kind of plan tomorrow.
Yeah. Please go ahead.
Yeah. So recently, instead of organics, those inorganics, in particular made of ytterbium, okay, emerged in this kind of paradigm, and they are not organic, so they can do kind of neutron measurement. And now people start seeing kind of continuum excitation in triangular anti-ferromagnet. Okay, so here is a kind of a list of recently kind of emerged triangular lattice magnet, and as you can see from literature, it's kind of quite recent. Many of them this year published this year. Okay, and they are made of ytterbium 3+, and the ground state is J1/2 doublet, equivalent to spin 1/2. Okay, but since they are F electron system, so interaction kind of much weaker, 2 to 6K. But many of them doesn't show any apparent ordering down to very low temperature, below 100 millikelvin. And those compounds, again, we have stack of oxygen, ytterbium, and oxygen, as I mentioned, like this. So this is kind of example of creating triangular structure made of sodium chloride structure. And this compound, ytterbium magnesium gallate, has been studied, quite enthusiastically over the last, 5 years. Okay, so there's kind of triangular lattice of ytterbium, okay, connected by other kind of element, magnesium, gallium. And let me mention, in this layer, you have, magnesium, gallium, but for some site, you have mixture of magnesium and gallium, giving rise to, some sort of disorder. But anyway, so measuring, specific heat, magnetization, they didn't find any magnetic transition well below 100 milli-K. Although energy scale of interaction is 4K, and they claimed it's quantum spin liquid. Okay, so no ordering down to 100 milli-K. And at that low temperature, they measured magnetic excitation. Okay, and this is kind of magnetic excitation at different energy, and you immediately notice this excitation is kind of a broad, extended over Q space. It doesn't look like a line expected, for Magnon excitation. Okay, and they say this kind of broad excitation extending over Q space and the energy is kind of a continuum excitation. And they assume the Fermi surface of spinon like this, they say they can account this pattern quite reasonably. So therefore this is kind of evidence for spinon Fermi surface. Okay. And the other group after 1 year reported quite a similar feature, extended kind of broadly over Q and energy, and quite a similar feature as kind of previous report. But this specific case, they applied magnetic field and made compound ferromagnetic. Then you are supposed to see where they find the Magnon dispersion line. But somehow even ferromagnetic phase, those people observed kind of broadened the Magnon excitation, like continuum, and so they suggested this disorder due to mixture of magnesium and gallium might play some role. And then kind of a theorist start saying, if we have randomly quenched a singlet over space, not dynamically, quantum mechanically fluctuating dynamics, but statically kind of a quenched singlet class can account many of experiments observed. Yeah, because of random distribution, you have continuum excitation. And to support this, other people measured kappa over T, and they see kappa over T go to almost zero, no finite kappa over T. So that means no iterant spin-on Fermi surface there. Okay. So in that sense, situation is somehow quite chaotic, unfortunately. So it's great, we start discussing continuum excitation spin-on Fermi surface, but because of disorder, it's quite hard to identify continuum excitation. And of course, the other compound claim to be a quantum spin liquid with a similar structure. And in some cases, they observe the continuum, but still, we cannot completely rule out the possibility of disorder. Maybe this, compound recently kind of proposed, cobalt 2 plus J1 half, discovered by Bob Carver. They find, finite kappa over T for this compound, suggesting iterant excitation in the insulators. So in that sense, they might represent kind of a best compound, but unfortunately, nobody has done neutron inelastic scattering measurement on this compound yet. Okay, so that's the situation. Okay, maybe today, I should stop here, and tomorrow I'm going to start from Kagome, and then go to Kitaev and physics of electron correlation and spin coupling. But let me quickly show kind of summary of today. No. Yeah, so I hope you agree, quantum spin liquid is one of the most exotic state of electric matter, seemingly silent, but hidden fluxionized excitation called spinons. And now it's kind of theoretically likely we have quantum spin liquid even in 2D and 3D. And we have quite rapid, progress of materialization recently. Okay, I forgot the without out. Okay, so many compound, sorry, without apparent magnetic ordering has been kind of discovered in organics, inorganics. Okay, triangular lattice, and I didn't speak, but Kagome lattice. And we see some signature of spinons, including continuum of excitation, finite density of energy excitation, like finite T-linear term in specific heat, thermal conductivity. They're kind of captured. That's kind of good news. But bad news, it's somehow, we have to admit the existence of a spinon Fermi surface has not been established yet completely, because of possible role of disorders. And disorder kind of masking to detect mobile spinons in their compound. And that's kind of a task, we experimentalists should tackle in future. Okay, thank you very much for attention. And may I take a question now?
Okay, thank you very much, Professor Takagi. For the audience, it's now time. You can ask any question. If you have any question, please unmute your microphone and shout. Oh, here we have one question at the chat. Can you read it, Takagi-sensei?
Let's see, okay. Okay.
Yuan Shan.
Yeah, Yuan Shan, okay.
You can speak out.
In what level can the Fermi surface language emitters apply to spinon? For example, a constant number of spinons in contrast to constant number of electrons. Yeah, so as far as I understand, okay, only very simple, spinon language you can find is, this 1D XY case. That case, we have, non-interacting fermions. Okay, so, Hamiltonian can be written with, non-interacting fermions representing spinons. And we have a definite, band. And in this case, in the ground state, number of fermion is, number of spins. Okay, so it's kind of half field. So in that sense, we have, constant number of electrons. Okay, but if you go other case, we have to introduce a kind of interaction between kind of spinons, and it's quite complicated. And maybe even metal, if you have interaction, it's not easy to describe a metallic state, except for kind of a Fermi liquid. And we have even more complicated situations in the spinon language.
Okay. Is there any other question? If you are shy, you can just type it in the chat, or you can just unmute and shout it.
Thank you very much for the talk. And I've got a question. So in RVB materials, what are the factors that determine the effective range of the interaction? Because you said there are short range RVBs and long range, and they have different gap sizes and so on. So I was wondering.
Sorry, could you speak up?
Oh, sorry. So in RVB materials, what are the factors that determine the effective range of these interactions? Because like, as in, when do we have a short-ranged RVB and when do we have long-ranged?
That's a very question, but you know, they are not, you know, well kind of established, you know, quantity. So maybe I can give you a kind of a concrete answer to that.
I see it. Thank you very much.
So maybe I can ask something. Nobody has a question. So is there any electric analog to this system? Like if I have ferroelectric and anti-ferroelectric, and I also have this sort of liquid just with the electric dipoles and not with spins?
So are you talking about you know, kind of liquid state of electron dipole, electric dipole? Yeah, okay. So that's kind of related to ferroelectrics.
Yeah, exactly.
Yeah. So like ferroelectrics, you know, in many cases, you have can order the state of you know, ferroelectric moment. But there is a, you know, class of, you know, material called quantum paraelectrics, and they have kind of fluctuating moment down to, you know, t equals 0 limit. That is called quantum paraelectrics.
Okay, I'll look into it. Thank you.
But of course, you know, they are, you know, electric dipoles. So, you know, yeah, of course, there must be some common physics, but you know, I'm not sure, you know, whether, you know, they share complete the same, you know, physics as, you know, magnet or not. Yeah.
Masashi?
Yes.
I think we should wrap up at this point because you will have a long question and answer session tomorrow. So if people have more questions, they can ask them. But the moderator is Masashi, but I don't know. He seems to be okay. I don't want to take over the role of moderator, but okay. So I think we should leave it at this. And
Okay.
thank you once again very much. And then we'll see you tomorrow again.
Yeah, for Masashi, it must be dinner time now. So.
Okay.
Okay. Thank you very much, and see you tomorrow.
Bye.